Hello everyone. Today I will be giving a talk in Reed Muller workshop on a presentation of polynomial formal verification of adder circuits via answer-set programming. Before we start, I would like to acknowledge that this work is supported by German Research Foundation DFG and Reinhard Kozelek Project Polypod. For our motivation, designing complex circuits nowadays require an efficient formal verification. However, the traditional techniques fail to provide an upper bound for the time complexity. Therefore, polynomial formal verification, or PFV, was introduced to address this issue. And for our contribution, we present an approach to verify an adder circuit using cut widths, and we indicate by our result that for a fixed cut width, a verification process can be carried out in a linear time. So for the presentation structure, first we start by going through some background knowledge such as ASP, adder function, and cut width property. Second, we explain our approach in terms of an example where we use an AIG representation of adder circuit. Then we analyze our time complexity of the approach, and finally we use an experimental result to confirm our theoretical one. So ASP. ASP is a form of declarative programming that describes NP-hard search problems where these search problems are reduced to compute answer sets. And for the syntax, given a set of atoms A, a logic program B consists of a finite set of rules, where each rule has the following form: A0 left arrow A1 to AM as a positive set of atoms, and AM plus 1 to AM as a negative set of atoms. And as an example, we consider a logic diagram of half-adder. We can encode it in the following program, where the set of rules in the first line represent the sum function, and in the second line represent the carry function. For the semantics, so the semantics is defined in terms of a reduct. So given set of atoms X, a program P under X contains only a rule with their positive atoms if only this rule contains no negated atoms in X. And finally, X is said to be a stable model or an answer set if X is the minimal number of atoms that correspond to a model of program under reduct. So for instance, the following program contains only three answer sets: AS, BS, A, B, and C, which correspond to ones in the truth table. So for the adder function, given two inputs A and B of size n and their initial carry value, the sum and carry function can be characterized in the following formulas. Now for the cut widths, informally, cut widths represent the minimum number of cuts that we require to partition the graph into two or more subgraphs. And in the context of the formal verification, circuit is said to be a k-bounded circuit if a circuit can be partitioned into disjoint subcircuits, such as each subcircuit contains at most k inputs. So we consider an AIG representation of a circuit, and we use this example through our presentation, which is a carry look ahead of size 2. And as we can see that since the adder circuit contains three output gates, then it can be split into three subgraphs by taking one root node and traversing all nodes that are reachable from it. And now we can actually verify each subgraph independently by checking whether the value of output gate matches the adder function. However, there are some nodes that are evaluated multiple times. For instance, node 12 is evaluated in all subgraphs, and we refer to this node as a con node, and they are the nodes that are induced by the cut. So in order to evaluate each con node only once, we first start by construct the set of con nodes in each subgraph, and then we use these con nodes to reduce each subgraph. So how we do so? We use these con nodes to remove the nodes from subgraph that contain this con node in its root. So we basically traverse the graph up to the con nodes. And also now we have two types of inputs. One is the primary inputs that occur in the initial graph. We denote it as PIN, and the set of non-primary inputs or incoming con nodes. We denote it as CIN. And now, in order to enable evaluating each subgraph independently, we would need actually to keep track of the values of con nodes. So it has to be stored, and we pass it basically to the later subgraphs. So roughly speaking, we use the carry function of the current subgraph to store the value of the outgoing con nodes. So first we introduce an injective function that maps each input pattern to a set of outgoing con nodes. Second, we use a surjective function that maps the value of outgoing con nodes to the value of the carry function. And the result of both functions, we store them in a hash table. Now for each reduced subgraph, we have two tasks basically. One is to verify whether it matches the other function, and then we need to construct the hash table so it can be used in the later subgraphs. One thing that we have to pay attention for is that it could be the case that these non-primary inputs can be not only from the previous subgraph, it could be also from any subgraph in the previous one. So therefore, we need to actually go through over all tables before the one we are about to evaluate. And we store this, the resulting table is actually populated with the primary inputs, and we say that thus reduced subgraph is a valid graph if and only if for every input pattern the output gate matches the corresponding other function. Now for the time complexity, we can see that each subgraph relies only on the number of input nodes. More precisely, that we can actually verify the subgraph or the reduced subgraph in time of all 2 power number of inputs. Finally, by taking the maximum number of inputs in all reduced subgraph, we can see that the circuit can be verified in big O number of reduced subgraph multiplied by 2 power k. Now for the experimental work. So first we use 3 types of other circuits, different other architectures with various input size up to 10k bit. We also set the timeout to 1500 seconds and the memory limit to 8 GB. Now for the plot on the right, it shows that how each circuit or each other architecture scales over time. And for the table, it shows the maximum number of input nodes in any subgraph, which is indicated by k, and the maximum number of gates we can have in each reduced subgraph. As we can see that the time depends only on the upper bound k, and that it is scaled in a linear time. So, in conclusion, we have presented our approach that rely on cut width property. We also have shown that for a fixed cut width, the verification process can be done in a linear time. So, this is the end of my presentation. Thanks everyone for your attention and see you later.